Hello everyone and welcome back to a brand new video. So today we're going to be looking at this hard Putnam integral, of course from the Putnam Exam. I'm not too sure which year this is from, but it's the integral from 0 to 1 of x to the power of negative x dx. Now this is a difficult integral to solve, and you cannot solve it, to my knowledge, with the standard integration methods such as substitution. Maybe we've got a series expansion in there somewhere. Feynman's method falls short for me. I couldn't get it to work. But before we get into that, I do want to talk about last video. So I have read the comments of last video, and it's very, very clear that the music was way too loud in the background, and that is completely my fault, obviously. And I must apologise for it. It seems a lot of you were very vocal about the music being too loud. Some of you did enjoy it, but of course I completely sympathise with those who found it hard to concentrate on the last video because of the music. And so I do take all comments as genuine constructive criticism, and it will not happen again. We live and we learn from our mistakes. So for that reason, there will be no music in this video, so you've just got my voice to listen to. If you think no music is perhaps worse than quieter music, I don't know. We'll see. So before we do get in though to this, before we get into this integral, I want to just point out one comment from last video, and that's this comment right here. Because this was by far my favourite comment of them all, and it comes in from this fine gentleman here, and he says, "Adding music is obnoxious. Thumbs down. Do not recommend." Now you can read the next part. He does waffle on a little bit, but my favourite part of all was when he says, "Why the F do you think you can make such a unilateral choice for all your potential viewers of your video?" And well, brilliant question. I didn't realize I was making that choice by adding the music. But I have to apologize to this person. He seems very, very angry, and so, sir, hats off to you for first of all writing such a well-structured hate comment. I've done a bit of analysis here, but yeah, just that opening statement was really really impactful, and it grabbed my attention immediately, grabs the attention of the reader, and yeah, it makes them want to read on. So hats off to you, good sir. Anyway, let's get on with the integral. So we've got the integral from 0 to 1 of x to the power of negative x dx. Now this integrand, this function here, x to the power of negative x, is not really in a nice form at all. And so we're going to aim to change that a little bit. Okay, and what we're going to do is we're going to change this to the integral from 0 to 1 of e to the power of ln x to the power of negative x dx, like so. So hopefully you can see what I've done here. I've put the x to the power of negative x inside of the ln, and then raised that to the power, raised it into the power of the e, and of course e and ln, the natural log, are inverse functions, and so they would just cancel out in the event that you wanted to do that, and you would just be left with the original function that we had. So this is perfectly fine to do, and we have still got the same. We've still got the same integrand here. Okay, well now, using the wonderful laws of logarithms, we can move the power inside of the ln outside of the ln. And so what that looks like is we've got the integral now from 0 to 1 of e to the power of negative x ln x dx. Okay, now this is in a much nicer form. Now let's recall the series expansion for e to the x. Okay, so e to the x can be written as the infinite sum from k is 0 up to infinity. So the infinite sum of x to the power of k over k factorial. Okay, and so that's exactly what we've got here. Our x, if you will, in this case is our power up here. And so what we're going to do is we're going to rewrite our integral as the integral from 0 to 1 of e, no we're not, of the integral from 0 to 1 of the infinite sum from k is 0 to infinity of negative x ln x all to the power of k over k factorial. Okay, and of course dx outside. We can do a bit of work with this. Let's distribute this k power into the brackets here. So we've got the integral from 0 to 1 of the sum from k is 0 to infinity of, let's raise this negative 1 here to the power of k. So we've got negative 1 to the power of k. Then we've got x to the power of k. And then, of course, we've got ln of x to the power of k all over k factorial dx. Okay, so now we can tidy this up a little bit. If you would notice, the sum from 0 to infinity of negative 1 to the power of k over k factorial, well, this part right here, this is just a constant. That is just a number. And so, of course, we can bring that out to the front of the integral, because you can bring constants outside of an integral, of course. And so we're going to have the sum from k equals 0 up to infinity of negative 1 to the power of k over k factorial times the integral from 0 to 1 of x to the power of k times ln of x to the power of k dx. So we have tidied this up quite nicely. Now we have just got this integral to deal with. And, well, if you notice, it's not a very nice integral to deal with at all, because we've got this k here in the power of both the x and the ln x. If it was x ln x, sure, it would be an easier integral, but it's x to the k times ln of x to the power of k. And so that does make our life a bit harder, but we are just going to do a u substitution, okay? And so we're going to do the u substitution we're going to let u equal negative ln of x, and I'll show you why that negative is needed in just a few moments. So if we go ahead and differentiate this, we get that du equals negative 1 over x dx, and if we times it by x and that negative sign, we're going to get negative x du equals dx. And of course, well, what is negative x? Well, let's talk about that. So we have said that u equals negative ln of x, so that implies that negative u is equal to ln of x, which implies further that e to the negative u equals x. And so when we've got this negative x down here, we've actually got negative e to the negative u, oh, what happened there? E to the negative u du equals to dx. Cool. So let's go ahead and substitute in everything that we have just done for our substitution. Okay, so this is now going to be the sum from k is 0 up to infinity of negative 1 to the power of k over k factorial times the integral, and let's talk about the limits now. So the limits, okay, so when x is 0, well, we're going to get u equals negative ln of 0. Well, ln of 0 is negative infinity. So negative infinity is, of course, infinity. So we've got infinity when x is, as x approaches 0. And when x is 1, well, we've got negative ln of 1, so that's, of course, just going to be 0. And this was the crucial reason as to why we introduced this negative sign here. Because if we didn't introduce that negative sign, we would have had a negative infinity down here, and that makes our lives a little more difficult. And, well, what's the point in that? We want to make our lives easier for ourselves in all situations. Okay, so let's actually go ahead and do this substitution. So we've got the integral now from infinity up to 0 or I should say down to 0, but infinity to 0, of now x to the k. Now what did we say x was? We said that x was e to the negative u. So we're going to have e to the negative k u, like so. And then we've got this ln of x to the power of k to deal with. Well, that is just negative u to the power of k. So we're going to have negative u to the power of k. And then we've got this dx to sort out. Well, we said that dx was this down here, negative e to the negative u. So negative e to the negative u du. Okay, brilliant. The substitution is done. Okay, let's tidy this up ever so slightly. Well, what we can do is we can use this negative sign here to flip the bounds of the integral. So we're going to have the sum from k is 0 up to infinity of negative 1 to the power of k over k factorial times the integral from 0 to infinity now, because we've used up that negative sign to flip the bounds, of e to the negative ku, negative u to the power of k, e to the negative u du. Right, well, what can we do here? How can we sort this out a bit more? A bit better, sorry. I know. Okay, so let's, this negative u to the power of k, we can actually break that up a little bit. And we can rewrite this, okay? So we've got, again, the sum from k is 0 to infinity of negative 1 to the power of k over k factorial integral from 0 to infinity of e to the negative ku. Right, this negative u to the power of k can be split up into negative 1 to the power of k, u to the power of k, and then e to the negative u du, like so. Right, okay, well, let's talk about, well, we can see something going on here. We've got a negative 1 to the power of k there, and we've got a negative 1 to the power of k there. So when you get those two things times together, they're always going to be positive. You're always going to get a positive 1 as your answer, because the power of the negative 1 is always going to be even. And negative 1 to the power of an even number is always just going to be 1. And so these two things actually go ahead and cancel out. So let's rewrite what we've got. We have got the sum from k is 0 to infinity of 1 over k factorial times the integral from 0 to infinity of e to the negative ku. That's now gone, so we've got times u to the power of k. I understand that my k's and my u's look quite similar, so I'll change that. There you go. Times by e to the negative u du. Right, where do we go from here? Okay, well, one thing we can do is we can tidy up the integrand a little bit. We can join together this e to the power of negative ku and this e to the power of negative u, because they both include an e to the negative u. And so we can rewrite this as the sum from k is 0 to infinity, 1 over k factorial, times the integral from 0 to infinity of, now, if we join together those e to the power of negative u's, aka sort of, factor them a bit, skipping a few steps, we can actually just show that this is equal to e to the power of negative u times k plus 1, and then of course times u to the power of k du, like so. Okay, right, well, where do we go from here? Well, hopefully some of you out there may be able to see that this integral that we've got right here is suspiciously close to the gamma function. So if we write out the gamma function, we can see how closely related our integral is to the gamma function. So the gamma function, if we recall, so gamma of z, which is of course equal to the z minus 1 factorial. It's sort of the factorial function. Well, this is equal to the integral from 0 to infinity of e to the negative t times by t to the power of z minus 1 with respect to t dt. Now this is very, very close to what we've got. And what we can do is we can make a substitution. So let's say, we're going to say, let t equal u times k plus 1. Okay, because if we do this, when we differentiate, we get dt equals, well, we're just going to get k plus 1 du. And if we rearrange then for du, so this implies that du equals dt over k plus 1, like so. And if we go ahead and incorporate everything that we've just done in our substitution, one moment, if I just move that up there, well, we can see that we've got the sum from k is 0 to infinity. These infinity signs are getting worse and worse, aren't they? There we go. Times 1 over k factorial times the integral. Now, let's think about our limits for a moment. So when u is 0, well, what's t going to be? Well, t is going to be 0. When u is infinity, well, what's t going to be? Well, t is also going to be infinity. So the bounds haven't changed. Brilliant. Then we're going to have e to the power of negative t. And, well, what was u? So we've got this u to change now. So given that t was equal to u times k plus 1, well, that implies that u is just t over k plus 1, if we just divide by k plus 1 on both sides. So we've got t over k plus 1. And it's, of course, all raised to the power of k. And timesing it now by this du, which we, of course, said was dt over k plus 1. So times by dt over k plus 1, like so. Okay, we have successfully done utilized the substitution, and we are slowly getting to a form of the gamma function. And so if we distribute this k now into this bracket here, we get the sum from k is 0 to infinity of 1 over k factorial times the integral from 0 to infinity of e to the negative t times by t to the power of k over k plus 1 to the power of k. But then if we times that by this k plus 1 here, then that is going to be to the power of k plus 1 like that, and then dt. So hopefully you can see what I just did there. The k plus 1 to the power of k here and the k plus 1 here have sort of, because you're timesing those together in the denominator, the power of the k plus 1 is raised by a factor of 1, and so it becomes k plus 1 to as the power. Okay, right. Well, in relation to our integral here, well, it's with respect to t. So everything that isn't a t is a constant, such as this k plus 1 to the power of k plus 1. That is just a constant in our case here. So we're going to bring that out to the front. So we've got the sum from k is 0 to infinity of 1 over k factorial times by 1 over k plus 1 to the power of k plus 1 times by the integral from 0 to infinity of e to the negative t times by t to the power of k dt. Right, okay. Well, hopefully you can see how this is the gamma function. If I scroll back up and I bring this down, actually, to where we're working, if I bring that down, there we go. Hopefully you can see how it's in the same form. However, here, instead of z minus 1 indicating this, so instead of having z minus 1 factorial, and of course that t is raised to the power of z minus 1, we've just got k here. So this integral right here is equal to gamma of, and it's going to be, what's it going to be, k plus 1? Yeah, k plus 1, which is of course equal to k factorial. There we go. Brilliant. So this entire integral is equal to k factorial, so we can rewrite it now. So I'm going to get rid of the gamma function, just for a moment, so I've got some space. Here we go. So we've got the integral now, we've got the sum now from k is 0 up to infinity of 1 over k factorial times by 1 over k plus 1 to the power of k plus 1 times by the result of this integral, which is k factorial. Now hopefully you can see how this k factorial here and this k factorial here cancel each other out, and so what we get left with is the sum from k is 0 up to infinity of 1 over k plus 1 to the power of k plus 1. And if you want to re-index this, we could say let's pick a letter, any letter, I don't know, let's alpha, why not, equal k plus 1. Well, we can say that this is equal then to the sum from k equals 1, sorry, not k equals 1, alpha equals 1, up to infinity of 1 over alpha to the power of alpha, which is equal to, if we just rewrite this, the sum from alpha equals 1 to infinity of alpha to the power of negative alpha. And well, that is a beautiful result. If we formally write it out now, we can say that the integral from 0 to 1 of x to the power of negative x dx is equal to the sum from alpha equals 1 up to infinity of alpha to the power of negative alpha. There we go. That is an incredible result. The integral of x to the power of negative x between 0 and 1 is equal to the infinite sum of alpha to the power of negative alpha. I think that's incredible. Anyway, thank you everyone for watching. Sorry about the music in the last video. Yeah, thank you for watching. Hope you subscribe. Oh, thank you for 1,000 subscribers, by the way. Yeah, I reached 1,000 subscribers with my friends at the pub the other day when we were looking through that comment that I showed you at the beginning. Thank you for writing that comment. It provided us with a lot of entertainment. Anyway, thanks a lot.